In this video, we are going to go over a new form of proof and then prove the exterior angle inequality theorem. Let's go over the reasoning behind this proof. For indirect reasoning, you assume that the conclusion is false and then show that this assumption leads to a contradiction. And that contradiction could be a contradiction to a statement that we already know is true, such as a theorem, a postulate, or a contradiction to the original hypothesis. So the new proof we're going to learn is indirect proof, or proof by contradiction. An indirect proof, or proof by contradiction, is a proof using indirect reasoning. Let's go over the steps for an indirect proof. The first step is to assume that the conclusion is false. So if I have a statement, if it is raining, then I bring an umbrella, we assume that the conclusion is false. So I do not bring an umbrella. As opposed to I bring an umbrella, we would say, assume I do not bring an umbrella. And then you would show that this assumption leads to a contradiction of the hypothesis or fact. If it was a fact that I always carry my umbrella, regardless of what the weather is, we could say that our new conclusion contradicts that fact. Step 3, we have to conclude our proof and say that since that false conclusion, that I didn't bring my umbrella, led to an incorrect statement, then the original conclusion is true. So if it's raining, I do bring an umbrella. Now let's look at a few examples of indirect proof before we go ahead and prove the exterior angle inequality theorem. Here I have an if-then statement. If x is equal to 5, then 2x plus 1 does not equal 15. And we're going to prove this using an indirect proof. So our first step is to assume that the conclusion is false. So in this case, our conclusion is 2x plus 1 does not equal 15. Assuming that's false, that means that we're assuming that 2x plus 1 does equal 15. Why don't we solve this equation and see what x would be equal to? If 2x plus 1 is equal to 15, we can say 2x plus 1 equals 15. Subtract a 1 from both sides. We get that 2x equals 14. And when we divide by 2, we get that x is equal to 7. But our original hypothesis said that x is equal to 5. So this is a contradiction. Step 1, we assumed that the conclusion was false, so 2x plus 1 was equal to 15. In step 3, we showed it's a contradiction. We can now move on to step 3, which is concluding our proof. Since the false conclusion 2x plus 1 equals 15 leads to a contradiction with our hypothesis that x was equal to 5, then the original conclusion 2x plus 1 does not equal 15 is true. Let's look at another example. Here we're dealing with an inequality. This says that if 3x is less than 12, then x is less than 4. X is less than 4 is our conclusion, and 3x is less than 12 is our hypothesis. So our first step is to assume our conclusion is false. So assuming this is false, that means that x would be greater than or equal to 4. And since we're assuming that x is greater than or equal to 4, we have two separate cases. We have that x is either greater than 4 or x is equal to 4. So now we're going to have to contradict both of those cases. Let's go ahead and use a table to help us prove this. I want to take care of 4 and greater than 4 all in this one table. So we're going to start at 4 and go up to 7. So when x is 4, 3 times x, so 3 times 4 is 12. When x is 5, 3 times 5 is 15. X is 6, 3 times 6, 18. X is 7, 7 times 3 is 21. Already we've contradicted our conclusion in our table. So shown in the table, when x is equal to 4, 3x is equal to 12. When x is greater than 4, 3x is greater than 12. So for x equal to 4 or x greater than 4, then 3x is greater than or equal to 12. And that contradicts our hypothesis, which says that 3x is less than 12. So step 1, assuming the conclusion was false. Step 2, showing that that false conclusion contradicts with either hypothesis or fact. Now, step 3, we're going to conclude that the original must be true. So in both cases, our assumption leads to a contradiction, and therefore, x is greater than or equal to 4. Our assumed conclusion is false, which means our original x is less than 4 conclusion is true. Now let's do an indirect proof of the exterior angle inequality theorem. If you remember, the exterior angle inequality theorem says if an angle is an exterior angle of a triangle, then its measure is greater than the measure of either of its corresponding remote interior angles. Given angle D, then this is our conclusion. So step 1, let's assume that that conclusion is false. Assume that the measure of angle D is not greater than the measure of angle A, or the measure of angle D is not greater than the measure of angle B. That means that the measure of angle D is less than or equal to the measure of angle A, or the measure of angle D is less than or equal to the measure of angle B. Let's just look at the measure of angle D less than or equal to the measure of angle A. Then we'll have that the measure of angle D is equal to the measure of angle A, or the measure of angle D is less than the measure of angle A. So here we have two separate cases. Unlike the last example where we did a table and proved both cases in one instance, here we're going to have to look at the individual cases. So our first case is the measure of angle D equals the measure of angle A. Starting off, we can say by the exterior angle theorem, the measure of angle D is equal to the measure of angle A plus the measure of angle B. The exterior angle is equal to the sum of the remote interior angles. But in case 1, we stated that the measure of angle D was equal to the measure of angle A. So let's use substitution and substitute angle D in for angle A. So we have that the measure of angle D is equal to the measure of angle D plus the measure of angle B by substitution. And by subtraction, 0 contradicts the fact that the measure of an angle is greater than 0. And since this is a triangle, we know that an angle that has to be greater than 0. We have shown that case 1 contradicts by fact. Let's look at case 2. So again, we can say by the exterior angle theorem, the measure of angle D equals the measure of angle A plus the measure of angle B. And since the measure of angle A and measure of angle B are positive, since they belong in the triangle. Remember, our definition of inequality said for any real numbers a and b, a is greater than b if and only if there is a positive number c, so c is greater than 0, such that a equals b plus c. That's the definition of inequality. Looking at this equation, we can say that angle D is greater than A, or it's greater than B. And that's by that definition of inequality. And that, again, contradicts our assumption. So step 1, step 2, and now step 3. These same two cases can be proved for angle B, but it's redundant, so we do not have to prove those for angle B as well. So in both cases, the assumption leads to a contradiction. Therefore, the original conclusion is true. The measure of angle D is greater than the measure of angle A, and the measure of angle D is greater than the measure of angle B. And we have proved what we needed to prove. That if an angle is an exterior angle of a triangle, then its measure is greater than the measure of either of its remote interior angles. Also remember that there is not just a single way to write a proof. Let's take a look at case 1, for instance. Instead of saying that the measure of angle D is equal to the measure of angle A, let's use the measure of angle B instead. Using that, we might not use the exterior angle theorem. Visiting the picture, if we said that measure of angle D was equal to the measure of angle B, then we could contradict that by the converse of the alternate exterior angles theorem. Because these two angles are equal, that means that this line, BA, is parallel with this line, let's say CE, or AC. But we know that those two are not parallel. Even though we have a transversal and alternate interior angles that are congruent, AB cannot be parallel with CE because they have a common point A. And we know that two parallel lines will never intersect. And that would be one way to contradict that measure of angle D was equal to the measure of angle B. Just because I proved this theorem one way doesn't mean there's not many other options of how to prove this.